Okay, so this is just a quick rehash over what we were talking about before break, and that is the least square solution to ax equal b. Okay, and so our setup here is that ax equal b is inconsistent, and of course that means that b is not contained in the column space of a, right? Because if b were contained in the column space of a, then ax equal b would have a solution, because remember that a times x is a linear combination of the columns of a, right? So therefore, if we think about our four fundamental subspaces, column space there, I'll just put the column space and row space in, well, maybe the null space too. Okay, and this is our mapping x to ax. Okay, then we said that b is not contained in the column space of a, so therefore b is hanging out here somewhere. Maybe I should go ahead and say that this is the null space of A transpose. Okay, so the way we want to work this then is we want to find the best approximate solution and so we need to try to figure out what best is going to be. Okay, and so of course we know that if b is not contained in the column space of A, then the point in the column space that is closest to the column space of A is b hat, where b hat is the orthogonal projection of b into the column space of A, right? And again, now because b hat is in the column space of A, we know that there is a solution. There is a solution to ax equals b hat, and let's call that x hat. And so what we say then is x hat is called the least squares solution. The least squares solution. Okay, and remember now, x hat does not solve ax equal b. X hat solves ax equal b hat, where b hat is the projection, and so x hat is the domain entry, or whatever you want to say, is the x value or the x vector that minimizes the distance between the column space of A, which is A times x, and B. Okay, so another way to say that is that x hat is the minimum, or gives the minimum over all x. Let me rewrite that. Gives the minimum over all x in the domain of the difference between b and a times x. Okay, and so notice, by the way, that you could square this and it wouldn't change your answer any. And so that's what we mean by the least squares solution, is that we're minimizing this error. So you can think of this as like the error function. Right, the error function depends on x and then outputs a real number. Okay, so now of course the question is, how do we find x hat? How to find x hat? How to compute x hat? Okay, well, the idea here is that if we look at our picture over here, then we can write b as the sum of two things. B is the sum of b hat plus, let's call this z. fingers aren't working very good yet. Okay, so B is the sum of B hat plus C, where B hat is in the column space of A, and Z is in the complement of the column space of A, which is the null space of A transpose. Okay, so we know that B can be written as B hat plus Z. Okay, now Z is in the null space of A transpose, right? And also Z is equal to B minus B hat, right? And so therefore, because Z is in the null space of A transpose, we know that A transpose times B minus B hat must be equal to 0, right? A transpose times Z is equal to 0 is what we're saying there. Okay, so that means that A transpose times B minus A transpose times B hat is equal to 0, right? And let's go ahead and substitute in now for B hat, because A times X hat is equal to B hat. We can rewrite this as A transpose B minus A transpose times AX hat equals 0. And so now we get what's called the normal equations. And that is that A transpose A times X hat equals A transpose times B. Okay, and so this equation does have a solution, right? Because we're using, this is what X hat has to satisfy. So X hat satisfies the normal equations. Okay, and so let's summarize what we see here. Given AX equals B, multiply by A transpose first, and we get A transpose A, X equals A transpose times B, and then we solve this. Solve this for X hat. Okay? Of course, that's assuming something about A transpose A, right? We talked briefly about how to do this. Just one thing to notice here, when you're talking about this AX equals B, A is almost always going to be a long or a tall matrix. Okay, so this is going to be like your matrix A, vector X equals vector B here. And so when we talk about A transpose A, right, that's going to be a small square matrix. So A transpose A is going to be, if this is like, let's say this is m by n, where n is the smaller number here, then this is going to be n by n. Okay, and so when we're solving this matrix, we're asking the question, when will A transpose A be invertible? And we had talked about that. Basically, the upshot is that A transpose A is invertible if the rank of A equals n. In other words, if the columns of A are linearly independent. Okay, so in the case that the columns of A are linearly independent, A transpose A is invertible, and so therefore, how do we compute X hat? X hat is then A transpose A inverse A transpose B. Good, and so here's a formula for X hat, given that the columns of A are linearly independent. Good. All right. Of course, the last part of this we might ask is, what happens in the case where the matrix is not, or does not have linearly independent columns? And the answer is you can still solve. So if A transpose A is not invertible, we can solve the equation A transpose A times X equals A transpose B using row reduction. Right, just like we started the class with. Good. So in both cases, then we are able to solve for x hat, which is called the least square solution to ax equal b. Good. So in the next short video, I'll just go through a quick example of how we would do this using Matlab. All right. See you then.